The first law of thermodynamics is a version of the law of conservation of energy, adapted for thermodynamic systems. The law of conservation of energy states that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but cannot be created or destroyed. The first law is often formulated by stating that the change in the internal energy of a closed system is equal to the amount of heat supplied to the system, minus the amount of work done by the system on its surroundings. Equivalently, perpetual motion machines of the first kind are impossible. History. Investigations into the nature of heat and work and their relationship began with the invention of the first engines used to extract water from mines. Improvements to such engines so as to increase their efficiency and power output came first from mechanics that tinkered with such machines but only slowly advanced the art. Deeper investigations that placed those on a mathematical and physics basis came later. The first full statements of the law came in 1850 from Rudolf Clauses and from William Rankine. Rankine's statement was perhaps not quite as clear, indistinct as was Clausius'. A main aspect of the struggle was to deal with the previously proposed caloric theory of heat. Germain Hess in 1840 stated a conservation law for the so-called heat of reaction for chemical reactions. His law was later recognized as a consequence of the first law of thermodynamics. But Hess's statement was not explicitly concerned with the relation between energy exchanges by heat and work. According to Trussell, Julius Robert von Mayer in 1841 made a statement that meant that, in a process at constant pressure, the heat used to produce expansion is universally interconvertible with work, but this is not a general statement of the first law. Original statements. The thermodynamic approach. The original 19th-century statements of the first law of thermodynamics appeared in a conceptual framework in which transfer of energy as heat was taken as a primitive notion, not defined or constructed by the theoretical development of the framework, but rather presupposed as prior to it and already accepted. The primitive notion of heat was taken as empirically established, especially through calorimetry, regarded as a subject in its own right. Prior to thermodynamics, jointly primitive with this notion of heat were the notions of empirical temperature and thermal equilibrium. This framework also took as primitive the notion of transfer of energy as work. This framework did not presume a concept of energy in general, but regarded it as derived or synthesized from the prior notions of heat and work. By one author, this framework has been called the thermodynamic approach. The first explicit statement of the first law of thermodynamics, by Rudolf Clauses in 1850, referred to cyclic thermodynamic processes. In all cases in which work is produced by the agency of heat, a quantity of heat is consumed which is proportional to the work done, and conversely, by the expenditure of an equal quantity of work, an equal quantity of heat is produced. Clauses also stated the law in another form, referring to the existence of a function of state of the system, the internal energy, and expressed it in terms of a differential equation for the increments of a thermodynamic process. This equation may be described as follows. In a thermodynamic process involving a closed system, the increment in the internal energy is equal to the difference between the heat accumulated by the system and the work done by it. Because of its definition in terms of increments, the value of the internal energy of a system is not uniquely defined. It is defined only up to an arbitrary additive constant of integration, which can be adjusted to give arbitrary reference zero levels. This non-uniqueness is in keeping with the abstract mathematical nature of the internal energy. The internal energy is customarily stated relative to a conventionally chosen standard reference state of the system. The concept of internal energy is considered by Bailyn to be of enormous interest. Its quantity cannot be immediately measured, but can only be inferred by differencing actual immediate measurements. Bailyn likens it to the energy states of an atom that were revealed by Bohr's energy relation H nu equals n minus n. In each case, an unmeasurable quantity is revealed by considering the difference of measured quantities. Conceptual revision. The mechanical approach. In 1907, George H. Bryan wrote about systems between which there is no transfer of matter. Definition. When energy flows from one system or part of a system to another otherwise than by the performance of mechanical work, the energy so transferred is called heat. This definition may be regarded as expressing a conceptual revision, as follows. This was systematically expounded in 1909 by Konstantin Carathéodory, whose attention had been drawn to it by Max Born. Largely through Born's influence, this revised conceptual approach to the definition of heat came to be preferred by many 20th-century writers. It might be called the mechanical approach. Energy can also be transferred from one thermodynamic system to another in association with transfer of matter. Born points out that in general such energy transfer is not resolvable uniquely into work and heat moieties. In general, when there is transfer of energy associated with matter transfer, work and heat transfers can be distinguished only when they pass through walls physically separate from those for matter transfer. The mechanical approach postulates the law of conservation of energy. It also postulates that energy can be transferred from one thermodynamic system to another adiabatically as work, and that energy can be held as the internal energy of a thermodynamic system. It also postulates that energy can be transferred from one thermodynamic system to another by a path that is non-adiabatic, and is unaccompanied by matter transfer. Initially, it cleverly refrains from labeling as heat such non-adiabatic, unaccompanied transfer of energy. It rests on the primitive notion of walls, especially adiabatic walls and non-adiabatic walls, defined as follows. Temporarily, only for purpose of this definition, one can prohibit transfer of energy as work across a wall of interest. Then walls of interest fall into two classes. Those such that arbitrary systems separated by them remain independently in their own previously established respective states of internal thermodynamic equilibrium, they are defined as adiabatic, and those without such independence, they are defined as non-adiabatic. This approach derives the notions of transfer of energy as heat, and of temperature as theoretical developments, not taking them as primitives. It regards calorimetry as of derived theory. It has an early origin in the 19th century, for example in the work of Helmholtz, but also in the work of many others. Conceptually revised statement. According to the mechanical approach, the revised statement of the first law postulates that a change in the internal energy of a system due to any arbitrary process that takes the system from a given initial thermodynamic state to a given final equilibrium thermodynamic state can be determined through the physical existence, for those given states, of a reference process that occurs purely through stages of adiabatic work. The revised statement is then for a closed system, in any arbitrary process of interest that takes it from an initial to a final state of internal thermodynamic equilibrium. The change of internal energy is the same as that for a reference adiabatic work process that links those two states. This is so regardless of the path of the process of interest, and regardless of whether it is an adiabatic or a non-adiabatic process. The reference adiabatic work process may be chosen arbitrarily from amongst the class of all such processes. This statement is much less close to the empirical basis than are the original statements, but is often regarded as conceptually parsimonious in that it rests only on the concepts of adiabatic work and of non-adiabatic processes, not on the concepts of transfer of energy as heat and of empirical temperature that are presupposed by the original statements. Largely through the influence of Max Born, it is often regarded as theoretically preferable because of this conceptual parsimony. Born particularly observes that the revised approach avoids thinking in terms of what he calls the imported engineering concept of heat engines. basing his thinking on the mechanical approach, born in 1921, and again in 1949, proposed to revise the definition of heat. In particular, he referred to the work of Constantin Carathéodory, who had in 1909 stated the first law without defining quantity of heat. Born's definition was specifically for transfers of energy without transfer of matter, and it has been widely followed in textbooks. Born observes that a transfer of matter between two systems is accompanied by a transfer of internal energy that cannot be resolved into heat and work components. There can be pathways to other systems, spatially separate from that of the matter transfer, that allow heat and work transfer independent of and simultaneous with the matter transfer. Energy is conserved in such transfers. Description: the first law of thermodynamics for a closed system was expressed in two ways by Clausius. One way referred to cyclic processes and the inputs and outputs of the system, but did not refer to increments in the internal state of the system. The other way referred to an incremental change in the internal state of the system, and did not expect the process to be cyclic. A cyclic process is one that can be repeated indefinitely, often returning the system to its initial state. Of particular interest for single cycle of a cyclic process are the net work done, and the net heat taken in, by the system. In a cyclic process in which the system does net work on its surroundings, it is observed to be physically necessary not only that heat be taken into the system, but also, importantly, that some heat leave the system. The difference is the heat converted by the cycle into work. In each repetition of a cyclic process, the net work done by the system, measured in mechanical units, is proportional to the heat consumed, measured in calorimetric units. The constant of proportionality is universal and independent of the system, and in 1845 and 1847 was measured by James Dewell, who described it as the mechanical equivalent of heat. In a non-cyclic process, the change in the internal energy of a system is equal to net energy added as heat to the system minus the net work done by the system, both being measured in mechanical units. Taking delta U as a change in internal energy, one writes where Q denotes the net quantity of heat supplied to the system by its surroundings and W denotes the net work done by the system. This sign convention is implicit in Clausius's statement of the law given above. It originated with the study of heat engines that produce useful work by consumption of heat. Often nowadays, however, writers use the IUPAC convention by which the first law is formulated with work done on the system by its surroundings having a positive sign. With this now often used sign convention for work, the first law for a closed system may be written. This convention follows physicists such as Max Planck, and considers all net energy transfers to the system as positive and all net energy transfers from the system as negative, irrespective of any use for the system as an engine or other device. When a system expands in a fictive quasi-static process, the work done by the system on the environment is the product, PdV, of pressure, P, and volume change, dV, whereas the work done on the system is PdV. Using either sign convention for work, the change in internal energy of the system is, where delta Q denotes the infinitesimal increment of heat supplied to the system from its surroundings. Work and heat are expressions of actual physical processes of supply or removal of energy, while the internal energy U is a mathematical abstraction that keeps account of the exchanges of energy that befall the system. Thus the term heat for Q means that amount of energy aided or removed by conduction of heat or by thermal radiation, rather than referring to a form of energy within the system. Likewise, the term work energy for W means that amount of energy gained or lost as the result of work. Internal energy is a property of the system, whereas work done and heat supplied are not. A significant result of this distinction is that a given internal energy change delta U can be achieved by, in principle, many combinations of heat and work.